Hello and welcome. In this video I want to show you more functions that we can find their integrals easier and faster with the tabular method compared to the integration by parts method. Look at these two general integrals, integral of e to the ax times by cosine bx dx, or integral of e to the ax sine bx dx. Consider these two integrals, which in these two integrals a and b can be any number. For finding these integrals, usually we use integration by parts method. But if you want to find these integrals with the integration by parts, you have to do lots of calculations. But with the tabular method, you can find these integrals easier and faster. Let me show you how. For example, suppose you want to find integral of e to the x cosine x dx. Again, I have to emphasize on this. If you want, you can find these integrals with the integration by parts, but it needs more calculations than the tabular method. But how we can utilize the tabular method to find these integrals? First, you have to make your table. For the tabular method, if you remember, we had three columns. The sign column, which always starts with plus, then minus, then plus, and so on. You had a derivative column. Always in the tabular method, we have a derivative column and integral column. Here, you can put e to the x, the exponential function, in the derivative column, or actually you can put the e to the x in the integral column. And you can put cosine of x in the derivative column and also in the integral column. And it works pretty well. Here I prefer to put cosine of x in the derivative column and exponential function in the integral column. But you can choose to put e to the x in the derivative column and cosine of x in the integral, and it works also in that way. Now we are going to take derivative of cosine of x. Derivative of cosine of x is negative sine of x, and derivative of negative sine of x is negative cosine of x. As you can see, if you continue taking derivative of negative cosine and so on, and you continue repeatedly, never you are going to get 0, because derivative of sine is cosine, derivative of cosine is negative sine, and so on. Never we get to 0. So there is a little difference between finding these integrals with the tabular method, with the integrals that we did in the previous video. If you watch the part 1 video about the tabular method, in that video, in the derivative column, we put the polynomial, and derivative of a polynomial finally after some steps gets 0. But here never we get to 0. So where we have to stop in these type of integrals in the tabular method, I will explain it in a moment. So just take derivative of cosine twice. Take integral of e to the x. Integral of e to the x is e to the x, and e to the x is e to the x. The answer of this integral is like the usual tabular method. We have to multiply the first function, the first expression in the derivative column, in the second expression in the integral column. Actually here all of them are the same, but always the rule in the tabular method is that to multiply the first function in the derivative column with the second function in the integral column. So the answer of this integral is e to the x cosine x. Then multiply the second function by the third function. Don't forget you have this negative and we have this negative here. So if we consider these two negative, they cancel each other. So we have what? We have plus e to the x sine x, or sine x times e to the x. But let me now tell you why I stopped here. When you want to use the tabular method for these type of integrals, you have to stop in a row that if you multiply the two functions in that row, you get something similar to the original function. When we multiply negative cosine of x by e to the x, their product makes something similar. Just the difference is a coefficient, this negative. So when we multiply the cosine by e to the x, we have the original function. You have to stop at that row. That was the reason that I didn't continue finding derivative and integrals. So here you have to stop. But what should I do now? Is this the answer of this integral? No. After you multiply the first function in the second function in the integral row, and you multiply the second function in the third function, now you have to put an integral. The reason that I put plus here is that I have a plus here. After you multiply the first function in the second function here, and second function in the third function, because you stopped at this row, you have to multiply these two functions by each other, but you have to put an integral for that. So you multiply this by the function in the same row, but integrate that. So plus integral of negative cosine of x times e to the x dx. So plus integral of e to the x times negative cosine x dx. I prefer to put this negative outside of the integral. So we have actually this. We can rewrite it this way. Let's review the process of tabular method. We make the table as usual in the tabular method, but the difference is that because never we get to the zero, when you multiply the first two as usual, you have to integrate the product of the function in the derivative column with the function in the integral column. So integral of, always at the end you have an integral. Integral of what? The product of the last row, the functions in the last row. So we have this. Now what we have to do for finding this integral? From this integral we got to the same thing. Attention, if I name this expression a, this is also a. Consider this expression, consider this as an equation. We want to find a, we want to find this integral. To find this integral, you can move this integral to the left, and attention, this integral is the same as the original integral. So if we move that to the left, we have plus, this minus becomes plus, of the same integral. So basically, integral of e to the x cosine x dx plus integral of e to the x cosine x dx. So we can rewrite it as 2 integral of e to the x cosine x dx equals to e to the x cosine x plus e to the x sine x. We get to this. By dividing both sides of this equation by 2, we can get rid of these 2 here. So if we divide both sides by 2, I have integral of e to the x cosine x dx equals to this expression divide by 2. And actually this is the answer of the integral. It needs a little practice to get familiar with the tabular method for these type of functions. But after you get familiar with this method, definitely this is easier than the old style integration by parts method. Let me show you another example of these type of integrals. Let's say we want to find integral of e to the power of negative 2 theta sine of 3 theta d theta. We make our table. Remember what was the table? Sine column, derivative column, integral column. Plus, minus, plus. In the derivative column you can put exponential or trig. I usually prefer to put derivative in the derivative column the trig function. and I prefer to put the exponential in the integral column. Derivative of sine 3 theta is 3 cosine 3 theta. Derivative of 3 cosine 3 theta is simply negative 9 sine 3 theta. What is integral of this? If you remember, integral of e to the x dx is e to the x. But when we have a coefficient here, like 2a in general, integral of e to the ax is 1 over a e to the ax. Integral of e to the ax is the e to the ax, but reciprocal of a you have to put in the answer. So what is integral of e to the negative 2 theta? Negative 1/2 e to the negative 2 theta. What is integral of negative 1/2 e to the negative 2 theta? Again, it would be 1/4 of e to the negative 2 theta. So finally, what is the answer of this integral? Based on the tabular method, we have to multiply the first function by the second by the third, and integral of this row. So the answer of this integral is multiply sine of 3 theta by the negative 1/2 e to the negative 2 theta. So it would be negative 1/2 e to the power of negative 2 theta sine 3 theta. Now multiply this by this. It would be what? Negative 3 cosine 3 theta times 1/4 e to the negative 2 theta would be negative 3/4 e to the negative 2 theta cosine 3 theta. And finally, the integral of this. Attention, we have a negative here. Times by positive would be negative. So minus, I prefer to put the 9 and 1/4, which multiply by each other, will become 9 over 4 as a coefficient outside of the integral. So minus 9 over 4 integral of e to the negative 2 theta times sine 3 theta. E to the negative 2 theta sine 3 theta d theta. Now look at this. This is the original integral that we had here. If I move this integral to the left, I have the original integral, and attention, the coefficient here is 1, plus 9 over 4 of the original integral. So it would be actually 1 plus 9 over 4 times by the original integral. 1 plus 9 over 4, if you do a simple common denominator, would be 13 over 4. So basically we have 13 over 4 integral of e to the negative 2 theta sine 3 theta. The theta is this. Negative 1/2 e to the negative 2 theta sine 3 theta minus 3/4 e to the negative 2 theta cosine 3 theta. To get rid of this, we multiply both sides by its reciprocal. Reciprocal of 13 over 4 is 4 over 13. So if we multiply this by 4 over 13, the answer of the integral is integral of e to the negative 2 theta sine 3 theta d theta would be, again, we want to multiply this by 4 over 13. If you multiply this number by 4 over 13, this would be negative 1/2 times 4 over 13. The 4 with these cancelled. So you have negative 2 over 13 e to the negative 2 theta sine 3 theta. And if you multiply this by 4 over 13, reciprocal of 13 over 4, you would have 3 over 13 e to the negative 2 theta cosine 3 theta plus c. So this is the answer of the integral. Maybe it seems that finding this integral with the tabular method is also hard, but actually, if you want to do this integral with the integration by parts method, with the original integration by parts method, it would be harder compared to the tabular method which I showed you here. I hope you liked this video and you learned the tabular method with watching this video. If you like this video, please subscribe in my channel and see you in the next videos.